Parfait. Donc bonjour, merci aux organisateurs de m'avoir invité à partager cette belle journée. Je pense que comme l'orateur précédent, je vais passer à l'anglais parce que je crois que les présentations vont être diffusées aussi sur Internet, donc ça permettra une audience un peu plus large. Alors, so I'm switching to English right now. And I'm going to talk about space-time metamaterials. So I also worked on meta-surfaces, and this is a book that we published on this topic about 2 years ago, with very useful synthesis techniques with connection with the electromagnetics of the unit cells and so on. And what I'm going to talk about is a bit different. It's also different from the reconfigurable meta-surfaces, because the surfaces we have seen, they are switched fairly slowly. So essentially, they operate in the static regime. And now the temporal variations here are much faster, fast enough so that the wave is completely transformed. Think of the Doppler effect, and of course the source moves at a velocity that is not negligible compared to the velocity of the wave, and as a result you get a shift, a Doppler shift, and so on and so forth. So just to give you an idea, we are talking about something that is fairly different. And I'm going to present here a generalized perspective of what I call a space-time engineered modulation, or GSTEMs for short. And so those are essentially a very hot topic currently in the metamaterial community and also in the optics community at large. And there are media that vary not only in space but also in time, as suggested here, by modulating a host medium parameter like the index of refraction. And they leverage latest metamaterial concepts and also some relativity, as you will see. And hopefully they can manipulate waves in unprecedented fashions. I'll try to show some examples. Okay, so and this is essentially based on that paper that was published in the AP magazine and that was elaborated with the help of my students here. I see the bottom is a little bit cut. I don't know if I can do anything for that, but let's try to continue this way. And so some background on motivation, and people working in metamaterials know that the history goes back to ancient composites, and then there were last century artificial dielectrics, and then at the turn of the century, modern metamaterials such as negative index and also cloaking. But really one of the latest and culminating point is the space-time metamaterials that I call here GSTEMs. And the reason they are very useful, they have so much interest, is they provide huge diversity. So you can imagine describing a material in terms of in a general tensor, chi, linking the excitation and the response. And you can classify metamaterials according to this. So the chi can depend from causality on the temporal frequency, as in negative index materials, 3D wires, double Lorentz, all dielectric, for instance. The chi, of course, can depend on the spatial frequency, like you have in diffraction gratings and chiral media, 2D wire, and of course, meta-surfaces. It can depend on the position. That's what you have in photonic crystals and photonic crystal-based waveguides and graded index lenses. But it can also depend on time. And this has been quite little used until recent years. And of course, introducing the time parameter enriches the possibilities of manipulation of light or electromagnetic waves in general. And this allows you to control waves both in the direct domain and in the inverse Fourier domain at the same time. And of course, we are mostly interested in having both space and time variations. They provide more opportunities than having only the time knob for the manipulations. So here I will present something with an emphasis on two aspects that are described in these papers. The first aspect is to describe those metamaterials under a common global perspective, which is the one of space-time. And we'll describe all the materials, pure space, pure time, space-time, and I will come back on that graph later, under this perspective. And then there is a line that is cut, but what that should say here is I will also extend the latest metamaterials that have a constant uniform velocity. Yes?
It's okay online.
Okay, good. To accelerated space-time metamaterials, so very crazy, exotic type of things. So that's the two things that we'll have here today. I'll put emphasis on that. So some fundamental electrodynamic aspects, and it pays off to first consider this in a broader context. You have different types of space-time system. You know, you first have sources moving in vacuum, And here the earliest contribution was done by Bradley, you know, with the Bradley aberration, whereby you see a star in a position that is tilted with respect to its actual position due to the motion of the Earth about the sun. And of course, you have the Doppler effect I already mentioned, you know, through the emission or reflection from a source with blue shift or red shift for approaching or receding sources. Then you have motion and matter. Now, in addition to these effects, you have two more effects. Now, moving matter is what? It means we have molecules and atoms that move, like a fluid, or like in a solid. And the two additional effects that you have is first the Fresnel Fizeau drag, whereby the light propagating in the same direction as the fluid is getting a bit faster and slower in the contradirectional direction. And also you have the magnetoelectric coupling, whereby if you bias by an electrostatic field a rotating system, then there is a magnetic field that is induced. And this is because of the rotating charges and corresponding electrical currents. So those are fundamental effects. And what we're interested in here is a third type of moving system, that's a moving perturbation. And in fact, this is what we have in conventional acoustic optic modulators. And what you have is you have a transducer, and here you have a moving index of refraction. And what you have is you have no motion of atom molecules. There is no net transfer of matter. What you have instead is just a perturbation that moves, and in this case, that would deflect the diffraction orders in a specific direction. But this can be largely extended to these space-time metamaterials, because instead of having just one dimension, you can have up to 4 dimensions, 3 dimensions of space and 1 dimension of time. And that velocity here doesn't need to be uniform. It can be modulated, it can be accelerated. And then you can have effects, as you'll see, as superluminality and exotic effects that don't exist in conventional systems. So it's important to distinguish moving perturbation and moving matter. You know, moving matter, you have a curling stone, and all the molecules and atoms move, and you have a moving frame that moves with the particle. In the contrast, in a moving perturbation, think of a laser-pumped system. The atoms and molecules, they only vibrate about their bound condition in the solid, and only the interfaces here move, corresponding to a traveling wave refractive index of that form, for instance. Okay, and now you can have a distributed version of that, so you can have a periodic modulation. Typically in metamaterials, the unit cell is small, but you have a propagation here that is like the velocity of light divided by the average index, and of course this is smaller than the velocity of light. And here you have, we discussed this in the break, the possibility of superluminality, because you can excite the structure from the top, you can polarize the silicon dioxide slab, and you see when the angle increases here, then the velocity of the point for a wave moving in this direction is getting faster and faster. And at the limit, you illuminate everything simultaneously, so you have what is called a pure time, or, sorry, an instantaneous modulation, right? Okay. So sorry for skipping that. So you can have superluminality, which is a bit unusual, by cheating a little bit. Now the moving perturbation is practically more interesting, you know, for micro-wave terahertz and optical technology than the moving matter. Let's look at some examples. You have the SINAC gyroscopes and the optomechanical devices in the moving matter. And on the other side, I mentioned already the acoustic optic modulators and the GSTEMs that I will present. So obviously, the advantages of the moving perturbation is you don't have moving parts. And as a result of this, you can easily attain relativistic velocities and accelerations that would be unthinkable here. And more than that, as I said, with the extra dimensions and different velocity regimes, then you can have novel physics that I will try to describe. Okay, some technical glitches. Okay, so, but let's see how the modulation really works and how we analyze it in the metamaterial regime. So let's take the simplest possible system. It's a surface acoustic wave in a piezoelectric crystal, and this is excited by interdigital transducers, and then you have areas where you have compression with higher index, areas with lower index of refraction, and this is moving along. So in a space-time diagram, you see here space and time, you can follow the crests and troughs. You see here the trajectories of them, and you have a period of this modulation in space and a period in time that are, of course, independent from each other, okay? So you have a space-time modulated index of refraction that moves along the structure. And if you are in the metamaterial regime, you're not only sub-wavelengths, as we usually say, but you're also sub-period, which means the modulation is much faster than the period, as I said in the beginning. And that's something like this. So you see the signal that you want to control is like this. And here you would have the spatial modulation, and here you would have the temporal modulation much, much smaller. So that eventually you have a bilayer unit cell structure that you can homogenize, and then you obtain a metamaterial model in terms of a tensor that, of course, depends on the velocity of this modulation right there. So now we have all the ingredients to come up with this general perspective of engineering the modulation for GSTEM. We can consider that we have pure space systems, just have a modulation in space. And this is the case of photonic crystals and conventional metamaterials. So here, this is the static case where the velocity of the modulation is 0. But then you can have pure time systems as illustrated here. Now the modulation is not in the space, but it's in time. And this is instantaneous. So this is the limiting case of a instantaneous system. And what we're more interested in is the space-time. You see here, this structure moves and the wave will be scattered in it. And here, these stripes have a slope that is inverse to the velocity. And so it's constant. So those have a uniform velocity. That's one category. And you can go more crazy, and you can make this slope varying. So now you have an accelerated system. And you can even have accelerations with non-zero derivatives, and that corresponds to things called jerk, snap, crackle, and pop. So very strange motions that are actually very practically useful. Okay? So this is kind of the two aspects I want to emphasize. First, there is this global perspective that considers all metamaterials in terms of their space-time structuration. And then this is very good to inspire unification. It did to many, many groups. By duality, you can find new time systems from the spatial ones, or space-time for either of the two. That has been very, very fruitful. And also this leads to a bridging with special and general relativity, where we can use the tools and do some more very unique things. And that's particularly the case in those type of metamaterials that are accelerated ones, which is what I will present in the end of this talk. Now let's look a little bit at the interfaces. I told you that the structure can be considered as made of stripes, and each of these stripes can be considered, if you wish, as a modulation atom or molecule, right? But the media between the stripes don't move, because the particles don't move. So the non-uniformity of discontinuity is entirely based in the interface, and therefore it pays off to first study the scattering that occurs at the interface. That's what we'll do first. Okay, and you find plenty of details in these papers. And let's start with the simplest possible thing. So a pure space discontinuity and a pure time. And we'll look at this in the direct domain and in the Fourier domain, the dispersion diagrams. So this is the simplest electromagnetic problem you can think of. You just have an interface, stationary, and then you launch an incident wave. Look, this is the space-time, right? So that's not an oblique angle. The wave is incident normally. So you launch a wave, and what do you have? You have a reflected wave and you have a transmitted wave, as we learned at school. And the corresponding Fresnel coefficients are calculated by ensuring the continuity of E and H tangent. The reason, of course, is because you have a special discontinuity. And if this is, if these fields are discontinuous, then you would have singular B and D, which is not allowed, right? So that's why we do that in textbooks. And then you can decide to look at the problem from the viewpoint of transitions, dispersion diagram transitions. The wave in the first medium is reflected on the other side and transmitted and compressed. So there is a variation of the wave number because there is a special discontinuity, okay? So that's what we do every day. Now, the dual is much less obvious. It was discussed by Molinaro at the Bell Labs. Now, what you see here, you have a system that varies only in time. So you have an earlier wave, and then you have a later wave that goes backward, and a later that goes forward. It's very different physics. And now to calculate those Fresnel temporal coefficients, you will do something else, because now you have a temporal discontinuity. So you need to make sure that these derivatives don't blow up to have singular E and H. So it's B and D that are continuous. So the electromagnetics is different. And now what you have is vertical transitions because you have a temporal discontinuity, you have a change in the temporal frequencies, the energies. So you see here you have an earlier wave and a later wave that is redshifted, and also a later wave that goes forward that is redshifted. Okay, so that's interesting, and this leads to new effects, like we suggested, what we call the inverse Newton prism. So Newton prism decomposes temporal frequencies into spatial frequencies. And if you do a perfect dual of this using these kinds of ideas, you would get something like this, where you decompose spatial frequencies, so angles, into different temporal frequencies. Okay, so something very funny and absolutely fundamental. Now we're interested not only in time variation, but space-time variation. And this involves a motion, this involves a velocity, and actually we can classify these structures into subluminal and superluminal, because you know now that this is something that can be done. So you see now you have a boundary that moves a little bit, and if you're subluminal, then you still have space-like refraction, reflected and a transmitted wave, but you can also have a superluminal scattering where you have later forward and later backward waves, right? And in this case, you have oblique transitions, a bit like in semiconductors. If you want analogy with silicon and germanium, you have oblique transitions in the energy diagram. So you have here, you see a Doppler shift, because there is a motion, and you also have a wave that is being expanded on the other side due to the contrast, the index of refraction. Okay? And notice here that you change both the wave number and the frequency, because we have a space-time discontinuity in electromagnetics. And this opens doors for plenty of possible applications, like pulse control, pulse compression on space and time, time reversals, and concepts such as space-time cavities and reflectors. So very, very novel things as far as I know. And then you can go one step further. Now you can decide to make these curves, so that's the interface here, curved precisely. That means that we have an acceleration. So in this case, the curve goes at the zero velocity, and then it accelerates up to the speed of light, or it can start instantaneous and then decelerate to the speed of light with some very interesting effects like inverse Unruh effect. And now the physics is more complicated, so basically the dispersion will depend on time, and there is chirping, not only change of frequency, but chirping effects that have been essentially not studied by anyone as far as I know. So now we have some idea of what happens at an interface, a space-time interface, and now what we can do is simply putting together, stacking the space-time interface, and then get to the full metamaterial structure. So we still see the striped structure, but eventually that will be homogeneous, right? Homogenized. So this is just to show you the fine atomic structure. So a good way phenomenologically to understand that is to consider the Bragg regime and the homogeneous regime, and also to start with the stationary case before the modulated one. So if we have a Bragg stationary structure, it's just a periodic structure like a photonic crystal. And what you have there is the Bragg scattering with a stop band where the reflection is one if you have no loss, and then you have this succession of stop bands. Now, if you have a moving modulation, this Bragg condition is altered by the velocity of the structure, and you can have in the stop band a reflection that is smaller than one or larger than one, depending on whether you are co-moving or contra-moving. You have then a cushioning effect or a smashing effect if you want to take a tennis analogy. Okay, so you have an active system. Now, if you are anisotropic but stationary, like in the wire medium, obviously the wave will see different structures in different direction. So you'll have a medium after homogenization that is anisotropic. And when you have now the motion on top of that, you have the Röntgen effect I showed in the beginning, so magnetoelectric coupling. So you have on top of this a chiral factor that depends on the velocity. So that's the most complex, but also the richest possible structure. And then if you do the math that you find in the papers, you can come up with a global medium tensor that depends on the velocity. Maybe another perspective is that of the frame hopping of relativity, where you jump from one frame to the other one. So if you look at your structure like this, remember the interfaces are moving, but the atoms and molecules don't. Only the perturbation moves. And so if you look at the dispersion diagrams, in the homogeneous regime, you could say that you should probably be between the dispersion curves of the two bulk media, and therefore you should have a isofrequency somewhere in between these two bounds. But it's very hard to predict where it could actually be. So you said maybe I should move to the frame of the interfaces, and if I'm in this frame now, the interfaces are stationary, but I see the molecules moving back in the opposite direction. And therefore, I break the symmetry of this dispersion, and you see the backward direction supports the Fresnel drag, the Friso drag. So the wave is accelerated in the direction of the stream. And so this velocity is increased, and that one is decreased. And now you see anisotropic, non-reciprocal dispersion curves. And what you have in this case is that if you launch a wave in one direction, the power is going to be deflected in a different direction. So you get an inhomogeneous wave with a deflection in the direction of the Fizeau stream. And it turns out that if you do an inverse transformation, you'll still have this kind of effect. And this is something that no one could predict, neither us. If you have a flow of water in this direction, the molecules of water, they push the beam that is sent this way towards the right? That's why you get the drag. But what we learn here is that if you have a modulation, in fact, modulation going this way, then the wave is deflected in the opposite direction. This is very counterintuitive. So I'll try to explain to you why this is so. It's simply a space-time averaging effect. So you see, if you have a pure space structure, then the wave spends the same amount of time in the medium 1 and medium 2 in the forward and backward direction by symmetry on average. So of course, you have the same backward and forward velocity. Now, if you have a space-time medium, you have the same slopes and velocities in the two media, because nothing happens in the media, but the medium is tilted. As a result, the wave spends a much longer time in the forward direction and the backward. So the backward is faster, okay? And that's the reason why we have this very unexpected deflection. We have an optical force that pushes that beam that is sent straight up, pushes it to the left against the velocity, something very unexpected. And this is helping you to understand, imagine you send a photon in a structure in the same direction as the velocity. You see, the photon is very slow because it needs to catch up with the medium in a sense. And if I replay this, if you send it in the opposite direction, then the photon goes much faster because the medium does part of the trip. It's just a matter of averaging, So some people thought this was Fresnel-Fizeau. Of course not. There is no motion of molecules in this system, okay? So it's really that type of effect. Now the next part, it's really going to another dimension, a crazy dimension. It's about acceleration. So, we have seen media that move with a constant velocity corresponding to that slope. Now we can do some acceleration, as suggested before, where the acceleration can be in the space, in the time, or both, as in this case. And we already know that by the equivalence principle, that means we are getting now to what happens in general relativity, a complex physics that governs our universe and the gravitational fields. But there is a difference. What is done in cosmology is that people study the propagation of celestial bodies, the motion of them, and the propagation of light in vacuum, in free space. So what we do here is we replace free space by this potentioid, it's a modulation with a different level of structuration. And then we really have scattering that is not in the vacuum, but in such a modulated medium. And this can be realized with some kind of tricks in the lab that I'm not going to expand too much on today. So this leads to actually a very powerful perspective of this media that interests cosmologists, which is the one of general relativity, as I said, where we have gravitation, heavy masses that bend, swallow, and chirp electromagnetic waves. The issue is you need to have masses many times the mass of the sun. That's not very practical, obviously. But there is this equivalence principle. Einstein says, look, acceleration cannot be distinguished from gravitation. And this inspired Ulf Leonard to accelerate matter instead of just using static gravitational matter, which is a very good idea, and to use the Fresnel-Fizeau effect. But this is also impractical, because you need to have huge amount of acceleration that would blast the entire setup that you do. So what we said in our group is let's try to accelerate a modulation instead. You see here, if you have curved phase fronts that ionize this silicon dioxide, then you have parts that go very fast and parts that go slower. So there are ways to create accelerated modulations. And then we are expecting to curve light as life is curved in space, because we know that if we have uniform velocity, we have deflection. And now curved space is nothing but locally straight space. So if we connect the dots, we expect to have a curvature, which no one has shown before. So it was a big deal for us to solve this problem. And you see here some of the results. That's the first time you show that you can curve light in a modulated system. But the first thing that you notice is the one we are used to. You see, if you put the modulation in one direction, then you have the global deflection in the opposite direction. Modulation in this direction, you have deflection in the opposite direction. And then you indeed see this curving, which was absolutely not trivial to us. So you have a curving against the direction of the acceleration. And this has been calculated by a full general relativity analysis, and this is extensible to other metrics. This is a simple matrix that is called the constant acceleration, where the velocity in the moving frame is constant. So there is a constant force. If you're in this frame, you feel a constant force in your legs in that rocket. Okay? But you can have circular ones and charged one, and I will show the Schwarzschild metric in the end. And then, of course, everyone in this room will ask, how are you in the hell going to realize this type of structures? That's challenging, but we are looking into the electronic and acoustic approaches. You can do that optically, mechanically, chemically. This is really very, very early, but we hope that there will be possibilities. Now, some of the early applications are what is called gravity analogs. And the community of astronomers and cosmologists, they have been doing things that we now call conventional gravity analogs. So this is one example you have heard of. It's Hawking radiation. And what is it? It's if you have photons at the horizon between the black hole and the outside, photon splits into its two antiparticles that are again photons. But one of the two is absorbed by the black hole, and the other one is expelled. And this is this emission is thermal radiation that is called the Hawking radiation. And this splitting is due to the quantum fluctuations of free space. So some people have tried in the laboratory to emulate this type of effects. They have done this only in one dimension. For instance, you see here a laser that is getting into a nonlinear cells, and on the periphery of the laser, you will get similar types of effects. Now, what we do, I call this GSTEM, accelerated space-time engineered modulation, gravity analogs, is a bit different. So here is an example. I promised you the Schwarzschild. Now, this is the matrix of a black hole, and you see when you have a black hole, the light is attracted by the hole and gets swallowed into it. So this is differential geometry. It takes you 1 year of full study to master that. And once you do that, you can calculate the permittivity and the permeability that the light sees in space, what made Einstein famous in one night, And so here is our result. I shouldn't say too fast, but what we do is we create a modulation, a secular modulation profile that generates exactly the same electromagnetic parameters. So the light that runs into the system sees the same thing as it would in space with this singularity. So the differences is here, people have been only mimicking horizon, so only boundary, but this is everywhere in space. So we have a fully fledged system of that type. And also, the people have been interested so far in classical cosmological effects like black holes, but now we can do nice things more. We can do superluminality. We can do white holes that don't exist because it's negative mass, but in the lab with optics and electromagnetics, we can do what we want, okay? So we have access to this fantastic physics. And here are some further, almost the end, further ASTEM opportunities. You know, I said you can, if you have no acceleration, you just have pure space and pure time. If you have velocity, then you have uniform velocity USTEMs, acceleration, but then you can have other systems. And let me show you just one example. You can have an arbitrary waveform generator, so you enter a pulse like a Gaussian, and then you find the proper trajectory of some kind of interface, and you can transform this into anything that you want. So this is illustrated here. You have a 1 amp channel, this is, and then you get a 2 amp channel at the output. This is just a proof of concept. So the boundary goes really back and forth and reshapes the pulses in this process. Another example that is a bit crazy is the one of space-time accelerated crystals. You know, crystals, they have horizontal stop bands, photonic band gap structure. Uniformly moving, they have oblique structures. Accelerated moving, they have oblique but inflated structures, you know, and that could be inflated and deflated to give some effects that, as far as I know, no one has ever studied. And here is another range of new class of electromagnetic problems also. Instead of having the conventional electromagnetic wedges and corners, you can have space-time ones. So you see here in space and in time, you have a wave, and you see here this is something like a space-time trap. So pulse comes here, it gets reflected, and then it gets trapped, you know, in this type of way. So those are canonical problems that electromagnetic theorists are welcome to join to solve. Just two practical considerations before concluding. The first one is there is no method available in the world, as far as I know, to study these problems. Unfortunately, neither commercial softwares nor in the literature. So we had to do our own codes, and that's, of course, for problems that are not canonical. We have solved some canonical problems mathematically, but most are not mathematically addressable. So what we do here, you see the Yee cell, we transform it. Instead of updating the usual electric and magnetic fields, we update the star fields, and these fields are auxiliary, they are not physical, and they automatically satisfy the relativity equation. So it's a bit like the Béranger PMLs, if you wish. We're using non-physical quantities to be able to solve our problem. And at each instant, we can transform back, okay? So if you insert this in the update equations, you know, the conventional update equations, they are augmented by this velocity-dependent type of things. And then you see here what happens if you have a simple pulse and the wave that is being scattered, the forward later and the backward wave. Here you have something a bit more complicated. And then you see a very complex scattering. It's because this is a very broadband pulse. And if you compare in this case with analytical results, you see a perfect result. So that can go into a commercial software if you wish. And the last comment is one that relates to what I would call space-time optics. Here we used an inspiration of the so-called Fresnel lens to reduce the size of the space-time system. You see, Fresnel has this fantastic idea of making a bulky, heavy lens much thinner, a bit like a metasurface, by just reproducing the proper curvatures. And there is the special case that is called a Fresnel prism, but it's just a particular case of that. So we say, why don't we do this not in space, but in space-time, as shown here, okay? It's a little bit hard to see what's going on, but it's something like this. You see, you send a wave in a system, and then you have this modulation that changes the refractive index, okay? Now, if you have a uniform modulation, you know, so this goes forever. And the size of your device, which I don't see here very well, you know, is infinite if you have a continuous wave. It never ends. So that's not practical. But using this inspiration, what you can do is you can refeed in the modulation in a periodic fashion that creates a space-time profile that is similar to the one of Fresnel, if you wish. And you see here a straight structure that is unlimited in space. You transform the frequencies through the change in the contrast. And here you do this on a shorter range, and you get what you expect. This is a little simulation. You see here the interface that moves, and then that comes back and goes periodically. This has been a big problem in this community because we need to have finite devices, obviously. Okay. So conclusions at this point, I talked about space-time metamaterials and their evolutions from ancient types to space-time systems. And I presented a generalized and extended perspective of the space-time systems. What I showed is the scattering in the direct and inverse space, so the different Fresnel scattering and also the horizontal or oblique transitions. Then we have seen how to combine these meta surfaces into a medium that we eventually homogenize, and we have space-time metamaterials. I showed this counterintuitive effect of contra-moving deflection of the wave and explained it in terms of just space-time averages. And then we also see that we have curving, so we can say that an accelerated modulated medium curves space-time for waves in a pompous fashion, if you wish. And then we have seen some general relativity type of effects and very early possible applications. I think the prospects are huge, at least theoretically, and in different areas that includes theory, different types of space-time geometries and analog computing. And for me, I'm starting a big program on quantum stems. I think this is maybe where they have the greatest future. I can say more about this if you wish. And then there is the modeling. You've seen just an FDT that just didn't exist in the picture of computational electromagnetics, and there are more sophisticated techniques that we might have to resort to. There is, of course, the physics, better understanding all these transitions. There is a regime that is called the interluminal regime. It's a bit like Cherenkov, but it's more than Cherenkov. No one has studied this type of effects, as far as I know. And then many possible applications, particularly, I think, to ultra-fast systems, quantum processing, and also hyper-broadband electromagnetics, just to mention a few. And that's the end. And I hope you are not too much in that situation, but if you are, please ask questions.